All right. Multiple choice for lesson 29. Question 1, we're looking for a motor that's has rotational inertia of 4.25 times 10 to the squared kilograms per meter squared. We're trying to find the energy that it takes to speed it up from rest to 112 rotations per minute. So first thing we need to do is figure out what our equation is. If we look on our equation sheet, our kinetic energy is 1/2 I omega squared. That means that we need I and omega. The problem gives us I here, and it gives us some version of omega here. So we just need to convert that and make sure that everything's in radians per second. So we have 112 revolutions per minute, and we have to convert this. So we have 2 pi radians per revolution, and then we have 1 minute is 60 seconds. So when we do all that, we get 11.73 radians per second. Then we just plug this in, 1/2 I, which in the problem, 4.25 times 10 squared kilogram meters squared, and then omega, which we just found, 11.73 per second. And when we solve all of that, we get 29,232 joules. So C is our answer there. All right, for problem 2, we have 2 identical objects starting at rest at the top of the same hill, one sliding without friction, and object B rolls without slipping. We want to know how fast their linear speeds compare at the bottom of the hill. So this is a conservation of energy equation. So we have kinetic translational plus kinetic rotational plus potential from gravity equals kinetic translational plus kinetic rotational plus potential from gravity. So at the beginning, they're both going to be at the top of some hill and starting from rest. So that means they're not moving. So at the beginning, neither of them has kinetic energy. So we just have potential energy from gravity. And then at the end, we're looking at the bottom of the hill. So at the end, there's no potential energy if we set 0 to be at the end. So we've got kinetic translational plus kinetic rotational for our 2 different objects. However, we said object A slides down without friction. So for A, we have no rotational motion. So all of our energy has to be translational energy. However, for B, let's see, this would be A, and then for B, we just have gravitational up front, but we do have this translational energy because it is moving forward, but it's also rotating. So we have both of those. So some kinetic translational and some rotational. So that means the linear speed of A has to be greater because all of its energy is in the linear direction. All right, for problem 3, we have the same situation here. We have potential energy has to equal translational kinetic energy plus our rotational kinetic energy, and all of that is our total kinetic energy, and that has to hold true for both of the cylinders, so the aluminum and the steel cylinder. However, if we break these down, this should be mgh equals our total kinetic energy. So what we need to know what the mass is at the beginning. And if we think about this, the steel cylinder has mass 2m. GH has to equal the kinetic energy. So we could say that this is the aluminum and this is the steel. So we know that the steel actually has twice as much kinetic energy as the aluminum does once it gets to the bottom. All right, and last problem here, number 4. We've got a ball rolling across the horizontal surface, and this is the important part here, without slipping. So that coefficient, and it rolls, right? That's also important. So we've got the coefficients of both kinetic and static friction. So how much work does friction do on the ball? Well, we got to think about this. How much work is friction actually doing? When we have a ball and we are rolling, so we've got our ball here and we've got the ground. It's only in contact at one point. As the ball rolls, maybe we'll use another color, and this point, you know, as the ball rolls this way, so if we were to draw this again, we have the ball here, and this time maybe the yellow dot's actually in contact with the ground, and the blue dot has gone on as it's rolling. So work, if we remember, work equals force times distance times the cosine of that angle between the two. So in this case, we have a force of friction that is acting on our object, maybe opposite the direction. Oops, I drew that backwards. Opposite the direction that it's rolling. So you have the force of friction there. Moving forward, but as that ball moves, that static friction is actually that ball is moving zero distance in contact with that same point. So our distance actually goes to zero because that force is changing the location on the ball that is acting, so it's not acting on the same thing as we covered distance. So work actually goes to zero when we're doing static friction and something is rolling. So we have 0 joules done of work.